Hello and welcome, SFU Math 152. It's Brenda Davison. This is section 10.2, Calculus with Parametric Curves. I'm going to try to go actually slowly through this section because it sort of provides a nice opportunity to combine a whole lot of things. And if you can go through this section and really understand how the arc length, the area, the surface of revolution is being computed here when we have our curves parametrically defined and when we use polar coordinates, you should be able to then sort of pull together and develop all of the formula for yourselves. And that, of course, means that it'll always be there for you whenever you need it. So it's a nice moment to try to bring together what we've been doing for the last several lectures. Okay, so this is section 10.2. We're going to try to find the arc length of the cycloid, and we're also going to try to find the area under the cycloid. And the cycloid, you can think of how the cycloid, the cycloid continues in this manner here. And you could picture how a cycloid is being made by imagining a piece of bubble gum stuck on a bike wheel. And then you imagine pedaling the bike and watching the path that the piece of bubble gum traces out. And then when that happens, you get this shape called the cycloid. Okay, it's sometimes used in bridge arches as well. We are going to label things in a very specific way. We're going to label the equation that defines the x coordinate as f of t. So x is going to be some function of t, which we're going to label f of t consistently throughout this thing, which in this case for the cycloid is r times t minus sine of t. And similarly, we're going to label y to be g of t. And that is, in this case, for the cycloid to be r1 minus cosine t. So a parametric curve is one where you have one function defining the x position and a different function defining the y position. And both of those functions have a common variable, which we call the parameter. In this case, it's t. Often we have it as t. And then when that t varies, we can calculate, for example, we could just imagine here t equal to, just pick some number, 0.1, and then t equal to 0.1 here. Then we would compute y, x, and y, and then of course that would give us a coordinate somewhere on the xy plane that we would be able to plot. Okay, so what we're doing is independently calculating the x and y coordinate, but we calculate each of them based upon a parameter t. So that is a parametric curve. It is just another way of providing the xy points that correspond to a particular graph. Okay, what we're going to do first here is we are going to talk about finding the area. And I'm going to actually, before finding the area here on the cycloid, I'm going to just do beside finding the area of something we already know how to do and that we've done in our previous lectures, and then move forward to doing that one, finding that curve parametrically, and then finding the area with the parametric description of the curve, and in order to try to make it clear what I'm doing before going for a more complicated curve like the cycloid. Okay, so we're going to pick the basic parabola. It seems to pretty much be a go-to example. So what we're going to do is we're going to attempt to calculate the area under the parabola between 1 and 2. So this is not the cycloid, but this is getting us to what we need to know so we can do the cycloid. So consider first this problem here. We have a parabola, and we wish to know what is the area between 1 and 2. So we want to calculate this area right here. And we know how to do that already. The area, would normally, this is the y-axis, this is the x-axis. What we have found is that the area here would be the integral from 1 to 2 of x squared dx. Okay, so that's a general statement of the fact that the area under a curve is the integral from a to b of f of x dx. Okay, that's the general formula, and this is a specific example for the parabola. Okay, so next thing I'm going to do is going to consider the same curve y equals x squared, but I'm going to define that same curve parametrically. So I'm going to now consider defining y equals x squared parametrically. Okay, there's many different parameterizations of any given equation. It's not a unique situation, but I'm going to choose. Well, what I'm going to do is I want to have x to be a function of t, and I want I'm not going to call it x of t. In fact, I'm going to call it f of t. So I want x to be some function of t, and I want y to be also some other function of t, and I'm going to have t range between alpha and beta. Okay, so that's so I don't confuse the alpha with the a, or I'm not going to label those two things the same. And now let us see how we can parameterize the parabola. Well, one way of doing that is to say have x equal to the square root of t and y be equal to t. So you can see that y is equal to x squared, and then t would have to range between 1 and 4. So when t ranges between 1 and 4, you see that x ranges between 1 and 2, which is what we had over here, and y will range between 1 and 4, which is exactly what we expect here. I mean, this is 1, and then this is 4. Okay, so this is right here. This is a parameterization of y equals x squared. Okay, now what we want to understand is how would if I did not know this, or I did not want to use that for some reason, and I was given this definition of the above picture, and I wanted to know what is the area under that curve, how would I do that? Okay, what do we know? Let's start with what we know. What we know is that the area, normally we would calculate it like this, a to b of f of x dx. Okay, what is f of x? F of x is y. So I could easily write this like this, a to b of y dx, because y equals f of x. Okay, now I want to point out that y is equal to g of t. That's that y right there. And then what is dx? That is the thing here. What is dx? So I have that x is equal to f of t. So if I take dx by dt, I get that is f prime at t. That's just taking the derivative with respect to t on both sides of this function right here, and that shows me that dx is f prime at t dt. So then I can see I make a complete substitution on the way I'm normally have been seeing this area formula. I make a complete substitution. I know what is y, I've identified that as g of t. I know what is dx, I've identified that as f prime at t dt. Now t ranges from, I need to cover the whole range. If x goes from, this is x goes from A to B, then t will range from, sorry, what did I put y there for? Goodness. X goes from A to B. And in order to have the whole area that we're attempting to integrate covered, I have to make sure that t goes from some other numbers, alpha to beta, such that when t goes from alpha to beta, x goes between A and B. Okay, so now I rewrite this area integral, what I would do for a parametric equation. So what I would do if I had an equation that's parametrically defined, then I'm going to take the integral, and this is now going to be t ranging from alpha to t going to beta, and y, this y here is g of t, and the dx is f prime at t dt. Okay, let us try that out with the example that we have happening here. We have a parameterization. We have right here f of t and g of t. So I'm now going to try out my integral on my parabola. That is, the area is going to be the integral. Now t ranges from 1 to 4. And then I have here g of t. That is the y, that is that thing right there, g of t. And then I have f prime at t, so I have to take the derivative. So I just want to be really clear here. In my example here, I'm using the fact that g of t, which is y, is equal to t, and then I'm going to use the fact that x is f of t, and that is equal to square root of t, which means that f prime at t is 1 over 2 root t. Okay, so when I take this integral here, this is going to be g of t times f prime at t, and that's going to be the integral from 1 to 4 of 1/2 root t. Okay, and then that's a simple integral. Right? That's going to be 1/2 times 2/3 t to the 3/2 evaluated at 1 and 4, and that number comes out to 7/3. So the area under that parabola I've calculated through my parametric description is 7/3. That is what I think. So this area here, I calculated it parametrically. I found that the area is equal to 7/3. Now let me just quickly check that. I claim that, of course, that is the same as the integral from 1 to 2 of x squared dx, which is 1/3 x cubed evaluated at 1 and 2, which is 1/3 times 8 minus 1, which is 7/3. Magic, it worked. Okay, so this is substitution. Substitution is an intensely powerful tool. So what I have done is just done a substitution. I've had this thing here. I've realized that these things are, I can define them in a different manner, and I have gone and made a complete substitution. I've generated an equivalent way of doing this. If I have my function defined parametrically, I will calculate the area using, I'm going to box this thing in because this is for, I think I probably have it later in my lecture notes listed out, but this is how you calculate the area of a parametric curve. Okay, and really a key point is this whole procedure that I've gone through is substitution. Okay, very powerful tool. Okay, so now we can find the area under a parametrically defined curve given its parametric description. All right, so now I can go back and here, and I wanted to get the area under this arch. Now it's not so easy for me to unparameterize this curve. So if I do want to actually know the area underneath of it, I am not going to be able to just say, okay, well, let me just go from the parameterization backwards to something I'm more used to and use that. That will not work here. So we're trying to find the area under the arch. So here I am, area under the arch. Area under the arch. So I've got that x is f of t, which in this case is r times t minus sine t. And I've got that y is g of t, which is r times 1 minus cosine t. I have now figured out that the oh yeah, let me just get let me also write out the range of the parameter here. Okay, that's the parameter is going from 0 to 2t, because as t goes from 0 to 2 pi, I think I said 2t, I meant 2 pi, then we've got this entire red curve here, and we have the full area that we are trying to calculate under one arch of the cycloid. Okay, I have now a way of calculating this given a parametrically defined curve. So the area under this cycloid is going to be the integral from 0 to 2 pi of g of t times f prime at t dt. So now I need to know what is f prime, and there is f of t is here. So I will calculate f prime of t as the derivative with respect to t of this guy here, r times t minus sine t. Okay, and that derivative is r times 1 minus cosine t. Okay, now I can set up the integral, and that is all. I'm actually not even going to solve the integral at this point. The key message here is how I go about doing this, not to evaluate a bunch more integrals. We've already evaluated lots of integrals, and by now that should not be a problem. So we're just going to get to the actual integral, and that integral is going to be the integral from 0 to 2 pi of g of t, r 1 minus cos t, times f prime at t, there it is, r times 1 minus cos t dt. And as you can see, that could easily be simplified. So the area under the cycloid is r squared times the integral from 0 to 2 pi 1 minus cosine t squared dt. Okay, so I can calculate the area under that cycloid as soon as I evaluate this, and this is it. This is a trig, obviously, a trig integral. You square that and use the you expand it out and then use the trig identity for cos squared. Just a momentary pause there. So this is a sort of a bigger idea and a nice idea, an application of substitution. Okay, so in keeping with that, we can actually we just did the area one in some amount of gory detail, but we now are doing the same thing for the other things we have been calculating in this course. So we have a function y of x, and then rather than leave it just as y of x, we parametrically define it, and we use two functions, and we calculate the x coordinate with some function f, and we calculate the y coordinate with some function g, both of which are functions of t. And then c is the corresponding parametric curve. Okay, we're having a little disclaimer here. Well, f and g have to be roughly nice. Okay, I mean, we're not going to have some bizarre functions for f and g. I mean, preferably we have ones that are, well, we will have ones that are continuous, and even it would be nice if they were differentiable too. Okay, so it isn't going to work for every possible choice of f and g, but we're just basically saying the functions are reasonable. Okay, reasonableness is where we're at here. Okay, all right, so let us then see, well, that's what I've just said here. If f and g are differentiable and the derivative of f is non-zero, then we have that via the chain rule, we have that dy by dx is equal to dy by dt times dt by dx, and that is equal to dy by dt divided by dx by dt. Okay, and what is dy by dt? Dy by dt is g prime at t, and dx by dt is f prime at t. That's where this is coming from. It's chain rule. Okay, so we have that relationship sitting there. We just saw in the previous slide that were we to calculate the area this way, we saw how to appropriately use a substitution, and we have the ability to calculate the area. Okay. Next, what do we do to calculate the arc length when we have a parametrically defined curve? Okay, we have a little, I'm gonna go tread lightly on these little things traversed exactly once. So with a parametric curve, you can move back and forth on the curve. If you're wanting to find the arc length, the length, you obviously only want to traverse the curve once. You don't walk back and forth on the sidewalk a whole bunch of times and then add up all that length and then claim that that is the length of the sidewalk, right? If you want to measure the length of the sidewalk, you walk down it once and then you measure that distance. That's what we're saying here. If your parameterization causes you to go back and forth on the curve, you only go and calculate the length of one path, one walk along the path. Okay, so here is from previous lectures. That is the arc length, and that is there sitting there the arc length differential. So now I want to see, I mean, I'm doing exactly the same thing I did on the other slide. I'm using substitution, and then I can rewrite and use this equation here to compute the arc length when I have a curve that's parametrically defined. So what do I have sitting up here? Right? I spend a little bit of time noticing I can get that from the chain rule. And what's there? Dy by dt over dx by dt is dy by dx. Okay, that right here is this here is dy by dx. Let's just make sure we're aware of that is dy by dx. So dy by dx, you notice dy by dx is right here. So dy by dx is g prime at t over f prime at t. So I can simply substitute that in. See, dy by dx is sitting there, so I substitute this in here. Because that is dy by dx, I can substitute this in here. I've already identified in the previous slide when we were doing the area what dx is. Dx is f prime at t dt. So I substitute that in here. And then I will come up with this formula here. So again, this is substitution. So what have we seen so far? Nothing is really any different. We just have to accept that we can represent a curve as y equals f of x, or we can represent a curve as x equals f of t and y equals g of t. And we are computing the same things, the area, the arc length, the surface area. We're computing those same things. And all we're doing to go from one set of formula to the other is substitution, and we've made use of the chain rule. The chain rule is very powerful as well. So again, I've got these two things here, and it is substitution. Okay, this is why I say if you can go through this slowly, assure yourself that you understand every step, and maybe even cover the lecture notes up afterwards and go through them when they're like, maybe get a fresh set of the lecture notes, download it again, and then say to yourself, you know what, I'm gonna go through this and attempt to develop each one of these formula myself, understanding all of the steps. This would be an extremely useful exercise. It would allow you to see how all these things are tying together. And what I don't want to is this to become is like, oh no, I have to memorize 42,000 different things, and what if I slightly mix something up? How am I even going to recognize that? You want to avoid that sort of memory trap. Okay, now that we've got the arc length, it's very, very easy to see what the surface area would be, and that is right here, sitting here for you. So this is what we saw in the previous lecture about how to calculate surface area when we're rotating about the x-axis, and that was 2 pi y, and then we have the arc length differential here. Okay, and so I mean the arc length differential, just like it did just above, becomes this thing here, and then what is y? Y is g of t. So this is extremely easy substitution. This I should maybe go just a little bit longer here. This portion here is exactly the same as above, and it becomes this portion here, and then the 2 pi y becomes 2 pi g of t, because y is g of t. Okay, there we have area, arc length, and surface area that we can now compute if we're given a curve defined parametrically. So we're going to now do a few examples, and actually we're going to start our examples by doing a tangent line computation. This is actually a calculus 1 tactic to find the slope of a tangent line, but we're going to do it with a parametrically defined curve just for a bit of review and seeing how we use the chain rule. So here's a curve, an asteroid. This curve is called the asteroid, and it is parametrically defined. So we've got it here. X is equal to a cos cubed theta, and y is equal to a sine cubed theta. Okay, and theta is the parameter. So theta is playing the role of t in our previous examples. It doesn't matter what you call the parameter. Theta. Okay, so what we want to now do is find the slope of the tangent line. Now we set it up so that we can find the slope of the tangent line at any value of theta. Just looking at this parameterization, I can see that, so example, when theta is 0, I'm going to get this point right here. This is theta equals 0, and at that point x is equal to a and y is equal to 0. So this point right here is a. Similarly, this is minus a, this is a, and this is minus a. Okay. All right, so we are going to find the slope of the tangent line. And the slope of the tangent line is dy by dx, and that is equal to dy by d theta divided by dx by d theta. Okay, that's the chain rule. So now I can compute dy by d theta. Let me do that over here so we can be clear. Dy by d theta is the derivative with respect to theta of y, and that is 3a sine squared theta cos theta. And then I can calculate dx by d theta, and that is d by d theta of x, and x is a cos cubed theta. And then that's going to be 3a cos squared theta times the derivative of the inside, which is minus sine theta. So I'll put the minus sign out there, sine theta. Okay, so I have dy by d theta and dx by d theta. So I will take, to get dy by dx, I will take the ratio. Dy by dx is the ratio of dy by d theta, 3a sine squared theta cos theta, divided by 3a cos squared theta sine theta. And lots of things cancel out, so this becomes minus sine theta over cos theta, and that is dy by dx is going to be minus the tangent of theta. That's kind of a nice result. So that's the slope of the tangent line. I think that is find the slope of the tangent line as a function of theta. I did that. There it is. Slope of the tangent line as a function of the parameter theta. At what points is the tangent line horizontal? I mean, we can look at this and see, look at the picture and see where there's horizontal tangent line. So I'm just going to write that down by looking, and then we can be a little bit more horizontal tangent. That is going to be when at these points a0 and minus a0. That's a horizontal tangent line. I mean, you can see that that's coming in here. You got a horizontal tangent line here, and guess where the vertical tangent line is? The vertical tangent line is here and here. Okay, so we have 2 places for horizontal, and we have 2 places of vertical tangent. That is going to be at 0a and 0 minus a. Okay, so I've answered the question by looking at the picture. However, I could be a little bit more mathematical, maybe. Or I don't know. I could do it from the because I know what the slope of the tangent line is. So horizontal tangent line, this one here. Why did I do it in blue? Because the one was in blue. The horizontal tangent line happens when this one here happens, of course, when the slope is 0. Slope equals to 0, and that happens when the minus, we know what the slope of the tangent line is. That is that there, and then we're basically asking where is the tangent of theta equal to 0, and the tangent of theta is equal to 0 when theta is equal to 0, pi, minus pi, etc. There's a whole bunch of those ones, but so we've got there, and so over here theta is equal to pi, and also for that matter theta is equal to minus pi here, and theta is equal to pi by 2 up here, and theta is equal to minus pi by 2 down here. Okay, so we have some values of theta there. Now, of course, I can, because I know how to calculate x and y, I can calculate the x and y coordinates. I'll just do this for one of them. So I'm going to take this guy here, and I'm going to say, okay, so what is the x coordinate? The x coordinate is going to be a times cosine cubed of 0, and that's a. And y is going to be a times sine cubed of 0, and that's going to be 0. So I get this thing right here. Okay. All right, so that's the horizontal tangent. The vertical tangent, I can do the same thing. The vertical tangent, when we have a vertical tangent line, that is when the slope is infinite. Okay, and that will happen. Let's see. I can't maybe see it totally directly. Right now I have the slope of the tangent line is minus tan theta. Let me rewrite it back out like this. That is sine theta over cos theta. So it will happen, the slope will become infinite when cos theta is 0. So I look for when cos theta is 0, and that would imply that theta is pi by 2 and theta is 3 pi by 2 or minus pi. So down here I'm 3 pi by 2 as well. Okay, so now I can calculate the x and y coordinates in the same manner from the parameter. Okay, so that I can easily check that what I drew by looking at the picture is indeed correct. Okay, at what points does the slope have tangent have slope 1? So you want to know when the slope is 1. Well, that's okay. Tangent line has slope equal to 1. So then I simply put the slope equal to 1. That will mean that the tan theta is equal to -1, and I ask where does that happen, and that happens theta equals minus pi by 4, and theta equals 3 pi by 4. And then I can see where then I calculate the x and y coordinates. For example, let me do it for the minus pi by 4 one, and that's going to be x equals a cosine minus pi by 4, and that is a over root 2, and then y will be equal to a sine cubed minus pi by 4, and that is minus a over root 2. So the coordinates of the point where the tangent has a slope 1 is going to be these coordinates right here. Slope of 1, a over root 2, minus a over root 2. Similarly with the other point I identified, I get minus a over root 2 and a over root 2. So where does the tangent line have slope of 1? Let us draw that on the graph. We can see where it is really. It has a slope of 1. No, that's a slope of -1, Brenda. The slope of 1 is right here. That is the slope of 1, and here. Okay, so that's slope equals 1, and we're going to do this problem as well. So when I just draw it on my graph while I'm here, this is where the that's a terrible line. I'm going to go here. This, I'm trying to come tangent to this point here. There it is, and tangent to this point here. So that is slope is -1 at this point here, on this line here, and on this line here. That's the slope is -1. Okay, so I found tangent line has a slope 1, and then tangent line has slope equals to -1. I simply set the minus the slope, which is minus tan theta. I set that equal to -1, and I observe that means that the tangent of theta has got to be equal to 1, and I do the same procedure. Let me just write down the points for you. You can verify this. Okay, so we have answered all the questions. So that is calculus 1 type of problem, slope of a tangent line, and that is something we can do now. We use a chain rule, and we can do it now with a parametrically defined curve. Okay. All right. I'm just looking at this next question here. Find the area under one arch of the cycloid. Also find the arc length. So we're back to the question that we did before. I did already go through a slide back how to find the area. So let me just write out where we got to, and then I'll just complete the project. In fact, why don't you try to complete the project from the beginning and then start the slide going, start the video going, and take a look at this slide, and this will be the rest of the details. So where did we leave this off? We used this. This is t going from 0 to 2 pi. I'm just writing t equals to emphasize that. That's g of t f prime at t dt. We had used that, and we had filled in all the necessary components. We have f of t and f of t, and here g of t, and we use those things appropriately, and we calculate that derivative, and we had done that, and we had gotten to here, 0 to 2 pi r squared 1 minus cos t squared dt. Okay, and as I indicated, what you do is you expand that square there, and you get 1 minus 2 cos t plus cos squared t dt. And that then we can integrate. We get r squared. In the first one we get t. The second one we get minus 2 sine t. And then we can evaluate those two things at 0 and 2 pi. And then we've got that integral of cos squared. How many times has this come up? My goodness, we have seen the integral of cos squared come up so many times. So we got to use that trig identity to do that. So I'm going to have here r squared. Now I'm evaluating this integral. I'm doing this right here. I get 2 pi. So I get 2 pi minus 0, and then 0 and 0. So it's just 2 pi. There's a 2 pi there. And then I have this integral from 0 to 2 pi. And then I replace the cos squared using the trigonometric identity 1/2 1 plus cos 2t dt, and that gets me r squared times 2 pi plus 1/2. Now I'm actually doing the integration, t plus sine 2t over 2, and that is going to be evaluated at 0 and 2 pi. Okay, nearly done. The area is going to be r squared 2 pi plus 1/2 2 pi, and that is 3 pi r squared. So the area under the cycloid is 3 pi r squared. Okay. We did not set up yet the integral for the arc length. Let us do that now. We've actually, I believe we've seen a similar, yeah, we have. And this is also going to be a bit of a review. I'm thinking here, and I'm going to try to find the arc length. So now I'm going to try to find the arc length of the cycloid. Okay, we saw the formula and how it comes about for the arc length, and that is going to be the integral from 0 to 2 pi. It's going to be the square root of f prime squared plus g prime squared, and then it's dt. Okay, f prime is r times 1 minus cos t. We calculated that earlier. G prime is I have r sine t. Let me make sure I have that right. G prime, yeah, I take the derivative of g. The derivative of r is 0 when I take the derivative with respect to t, and then I have derivative cos. Yep, it's r sine t. Okay. I will easily square both of those. Maybe I'll just do this in one step. So here, then the surface area is the integral from 0 to 2 pi. And I'm going to take the square root, and I'm going to square f prime, and I'll get r squared 1 minus cos t squared plus r squared times sine squared t dt. Okay, all is not lost actually here. It looks pretty, it's looking pretty hideous, but it's not so bad. We expand that, and then you see that you have sine squared plus cos squared. So that so then the cos squared t plus sine squared t, that's equal to 1. So I'm going to expand this thing and use that identity, cos squared plus sine squared, and then that will allow me to simplify this noticeably, and I will get that this integral is the integral from 0 to 2 pi of the factoring out the r squared outside of the square root, it becomes r, and I have underneath the square root 2 times 1 minus cos t dt. Okay, so it's a noticeable simplification. You may feel mildly alarmed when you see this integral, but it's not so bad because it needs to occur to you though that we have this identity here. Sine squared t is equal to 1/2 1 minus cos 2t. Okay, so that allows me to replace this with sine squared, and I can take the square root of that, of course, and get uh, sine. I can get just a sine. So I want to get a sine squared under there. I'm just observing that here. I'm being careful. I'm observing that I've got cos 2t here, but I've only got cos t here. So I'm going to write it like this: 2 sine squared t by 2 is equal to, this is just a substituting t by 2 for t. T by 2 is equal to 1 minus cos t. So you have to sort of massage the trig identity into a form that is exactly what we need here. So this then, when I substitute that in here, I'm going to get that the surface, the arc length is r times the integral from 0 to 2 pi of the square root of 4 sine squared t by 2, and then mercifully I can take that square root, so I get 2r, the integral from 0 to 2 pi of sine 2, like that, and I can careful not to leave off the dt, and I can integrate that, and I will leave those details to you because you know how to integrate this, and so this also just practice. You will find that this comes out to 8r. So the arc length of the cycloid of one arch of the cycloid is 8r. Arc length is 8r. Nice result. I think we've seen this this integral before in one of our previous arc length calculations. I can't remember, but somehow it's occurring to me that I've seen this come up, and feeling starting to sweat, and then realizing, oh no, clever use of that identity is going to solve the problem. If it's not the case, if I just remember the last time I did this, then that's fine. Now you've seen that. Okay, so trig identities coming up repeatedly. Okay, now we're going to try to find the area of the surface obtained by rotating the curve about the x-axis. So we're going to go across here. We're going to get some sort of a curve. Oh, let me change to blue. We're going to get some sort of a solid. It's going to look like this, like that, and it's going to have these circular cross sections here, like that. So that's what our solid is going to look like. And we're going to attempt to say, okay, we've got this solid. What is the surface area? How many square feet of paint do I need to buy to paint the outside of this thing? So we have an expression for the surface area. I'm going to call this again S. This is the surface area now. S is the surface area. That is going to be the integral from alpha to beta. That's where the parameter varies between alpha and beta. 2 pi g of t times the square root of f prime of t squared plus g prime at t squared dt. Okay. So that is the formula for the surface area. So in this particular case, g of t is 3t squared. So let's make sure that we're using the right notation, and x is f of t. So then I can fill that information in here, and I get the integral. Now I'm integrating with respect to t. T is going between 0 and 1, 2 pi, and then what is g of t? G of t is 3t squared. And then I have to fill in this thing here, f prime of t squared. So I'm taking the derivative of f, and I'm taking the derivative of that with respect to t. I get 3 minus 3t squared, and I'm going to have to square that. And then I have to take the derivative of this with respect to t and square that. So I get 6t, and when I square 6t, I get 36t squared. It's looking pretty ugly, actually, isn't it? Okay. Well, which way to proceed now? I mean, clearly you need to do a simplification on what you've got in here by squaring it out. For some reason, I'm thinking of when I did this. I made a substitution earlier on. I'm not sure if that's the way to go or not. Let me try this is always dangerous. I'm going to just try it differently than what I did. I just want to take a look at this this part of the integrand here and try to simplify it a bit. So that is going to be, if this doesn't work, I'll revert to a different method. So this is going to be 3 minus 3t squared all squared plus 36t squared. I'm going to square this out. That's going to be 9 minus, that's going to be 6. No, it's going to be, let's not make a mistake, 3 minus 3t squared, 3 minus 3t squared times 3 minus 3t squared. That's going to be 9, and then I get minus 9t squared and minus 9 squared, minus 18 t squared plus 9t to the 4. Okay, so that's going to be minus 18 t squared plus 9 t to the 4 plus 36 t squared. That's going to be 9 plus 18 t squared plus 9 t to the 4. And is that, let me think, is that equal to 3 plus 3t squared squared? I believe it is. Let me make sure. I mean, then I would be actually just doing this, changing these to plus signs, which would change that to a plus sign. And that's what I've got. Okay, that makes me super happy because then I take the square root of that. So I should then have been able to simplify this to this thing here. 0, 1, 2 pi times 3t squared times the square root of this thing squared. So that is nice because this is just 3 times 3t squared. Okay, now all my problems are solved, right? Well, I guess, yeah. So I've got, I feel very happy. I can then go like this. Let's get the constants out so I can stop thinking about them. That's going to be yeah, 3, 9. What has happened to my 2, 6? Have I lost? I'm thinking I might have lost a factor of 2. Is it possible? Let me think. I've got a 2 there. I've got a 2 here. I've got a 3 there. And then I'm going to factor out the 3 from here. That's going to give me 3, 9, 18 pi. That's going to be then t squared times 1 plus t squared dt. 2 times 3 times 3 is that's 18. The t squared is there. Okay. Now I can expand that 18 pi. This is, oh, maybe I'll do it in 2 steps. 18 pi integral from 0 to 1. I distribute the t squared. And I get this 18 pi, and then I can integrate 1/3 t cubed plus 1/5 t to the 5th, evaluated at 0 and 1, and I get s is equal to 18 pi times 1/3 plus 1/5. and that is going to be a common denominator of 15. It's huge amounts of stress doing a lot of arithmetic without doing it in advance because you think to yourself, it is so easy to make a mistake. This is going to be 5 plus 3, which is 8. And I got 8 over 15. 18 pi times 8 over 15. Not totally happy with that answer. I got 1/5 plus 1/3 times 2. Let's see here, 1/5. I get 3, 15, 8. I factor out a 3. Hang on a sec. I am thinking. That's why I get 2 there. I get 3 plus 5, which is 16 times 9 over. I got 16 times 11 over 15. I got 18 pi times 8 over 15. There's a 3 I can cancel out between the 18 and the 15. So that would become 6 and 5. And I would get, oh, I am now feeling very happy, 48 pi over 5. Okay, there we go. I got the numeric answer that I expected, going a slightly different method than when I did this problem previously. Okay, so I have got the surface area of this guy here. So the surface area is 48 pi over 5. Now you notice that what is important here when you start to see integrals like this is to, well, it's not to panic and crumple into a heap, which it's easy to feel like doing, is to try to carefully expand things, combine like terms, possibly use some identities, manipulate the integrand using algebra in order to simplify the thing down to where you can actually integrate it. It is very true that sometimes these things are difficult to deal with. Okay, time consuming too. Okay, and we're going to do one now with polar coordinates. So I mean if you want to think of it, you can think of it this way. Polar curves are just really a special type of parameterization. Really, that is where x is, the parameterization is x equals r cos theta and y equals r sine theta. Okay, so that is our parameterization that gives us this special type, which we call the polar coordinate system. So here we've got that cardioid. We've seen one of these guys before. What we want to do is find the arc length. So we want to find out how long is that blue line there that makes that heart shape. And we also want to find the surface area. We do want to do this, right? Okay, so how am I going to do this? I'm going to let's see, okay, here we go. Hold on to your hats. The arc length, I'm going to call that L. We know how to do this for a parametric curve. That is going to be the integral from alpha to beta of the square root of f prime squared plus g prime at t squared dt. Okay, x is equal to f of t, and well, in this case we're using the parameter theta, so I mean we've basically done this. That is going to be a true statement here, and that is in this case going to be r cos theta, right? And similarly y is r sine theta. Okay, and that is g of t. Now be nice and call it g of theta. Okay, so I mean t is theta. Theta is our parameter. We always use theta as the parameter in polar coordinates. Okay, so now I can calculate dx by d theta. that is, here, let me call it f of theta. That is f prime of theta. I'm going to change these. I think I'm just going to introduce confusion by having t and theta, even though they're the same thing. I don't sort of, sounds a bit odd if I just change my name midway through the lecture, but that is kind of what I'm doing. If I just change my name to Betty, and you know, halfway through the lecture you're calling me Brenda, and then suddenly you start calling me Betty, I haven't changed at all. I'm just as silly as I always was, and nothing underlying has changed. I mean, that's the same thing here when I just rename theta to be t. However, I recognize that it can introduce a bit of confusion, so I'm going to just change the formula to have the parameter that we're using here, which is theta. Okay, that is going to be, now I'm taking the derivative with respect to theta of x, so I'm going to get dr by d theta times cosine theta minus r sine theta. Okay, we have to recall that r is a function of theta, so we have to use the product rule. That is what's happening here. So r is a function of theta. It's not a constant, right? In fact, we know what the function is. R in this case is 1 plus cos theta. R is a function of theta. So this is actually true for all, these next few statements are true for all polar curves. So now I'm taking the derivative of this here, r sine theta, remembering that r is a function of theta. So this is sine theta plus r cos theta. Okay. So now I'm going to add together dx by d theta squared plus dy by d theta squared. And that is going to be equal to this thing here squared plus this thing here squared. Wow. It's not all is not lost though. I encourage you to do this with the algebra, and because so I'm going to square this guy here, like I said, and square this guy here. I'm going to add them together, and I'm going to use the trig identity sine squared theta plus cos squared theta equals 1, and that will then nicely simplify down. Actually, it's not so bad. Looks like this: dr by d theta squared plus r squared. And that's algebra. So this is algebra. Okay, so in general, I haven't made reference to the cardioid here. So in general, in polar coordinates, which is a special type of parameterization, I can calculate the arc length in this manner. There it is. Okay, now in particular, for this in particular, that is our case right here, where r is equal to 1 plus cos theta. That is because we're looking at the cardioid. This is the equation of the cardioid. Then dr by d theta is minus sine theta. Okay, now I can fill these things in. This will be the integral. I'm going to go halfway around. So I'm going to go from 0 to pi, and then I'm going to double it. I'm using the symmetry of the cardioid there. The cardioid is symmetric about the y equals 0 line. Okay, and then this is going to be the square root of 1 plus cos theta squared plus minus sine theta squared. Okay, that is these two quantities here. There's a bunch of algebra. Oh, maybe this is why I had in my head that we've seen this integral before, because here it comes again. This simplifies with trig identity sine squared plus cos squared is equal to 1. This simplifies to this thing here, 2 times 1 plus cos theta. And we just saw how to do that integral, right? We saw how to use the half angle identity to do this. Okay, so we can in fact solve this. I want you to do that same as we did in the previous previous calculation, and you'll come out and find out that that arc length is equal to 8. So that is the arc length of the cardioid. And then we could calculate the surface area. That is going to be the integral from some alpha to beta of 2 pi g of t. This is the general formula here. F prime at t squared plus g prime at t squared dt. And then we've already done this part here above, right? We just did that in calculating the arc length. So that makes it easy for us to write out the surface area integral. It is the integral from 0 to pi. I have to be careful here. I don't need the 2 because I'm revolving it about the x-axis. I only have to go from 0 to pi to catch the whole thing. So this is going to be 2 pi. What is g of t? That is r sine theta. That is y. And then I already know this here. This is well, this is still actually, this is still in general. Let me be careful here. This is true for all polar curves. This is r squared plus dr by d theta all squared d theta. Okay, so then I can fill in the what I need to do here, and that is I'm going to go from 0 to pi of 2 pi, and what is r? R is 1 plus cos theta. So this is in general, and then this is for the cardioid, and that's going to be there. And then we've already figured out what this thing is. It's 2 times 1 plus cos theta d theta. Okay, so now we've got an integral that we can evaluate because we know we can get rid of this thing, getting a sine function, and then we can do some substitutions and do this. Okay, so this is to be completed by you. I don't want to go on any longer in this lecture. The theoretical stuff is done. Completed by you, a somewhat tricky integral, but the more practice, the better. Okay, I'm going to be back, and we're going to actually leave this topic and move on to a new topic, and that's going to be talking about some differential equations. Thank you. Bye-bye.